Our solar system lies right at the center of a relatively empty region in space. This cavity has an extremely low particle density, at least 10 times lower than the average density of the interstellar medium in our galaxy. But at the same time, it contains a thin gruel of high-temperature X-ray-emitting plasma that can range up to 1,000,000 degrees. This cavity is known as the local bubble and is home to our Sun and thousands of other neighboring stars. But how did we discover this bubble? How did it form in the first place? And most importantly, when did the Sun enter it? First of all, the shape of the local bubble isn't spherical, so referring to it as a bubble is a bit inaccurate. Instead, it appears to have an hourglass shape that is narrowest in the galactic plane and widens above and below the plane. Furthermore, the bubble seems open-ended and bursts into the galactic halo in the direction away from the galactic plane. Finally, it has a diameter of about 1,000 light-years, and on its boundaries, it is surrounded by an envelope of colder, denser, and neutral gas and dust. Inside this cosmic void, several cloudlets of the interstellar medium and cosmic bodies are oriented in sheet-like structures near the bubble's boundary. Along with several other neighboring stars, the Sun is currently embedded in a group of cloudlets known as the local fluff complex. Then, some tunnels appear to branch off from the local bubble through the surrounding dense gas and open out into other cavities. One can picture these interconnecting cavities and tunnels as analogous to the holes we see in a typical sponge. The local bubble was discovered in the 1970s and 1980s using a combination of optical, radio, and X-ray astronomy. However, for years it remained unknown how such a structure formed in the first place. Over the years, different missions were launched to study the anatomy of the bubble. It was a prime region of interest for the Extreme Ultraviolet Explorer mission, which ran from 1992 to 2001 and examined hot EUV sources within the bubble. Then, in February 2003, a small space observatory called Cosmic Hot Interstellar Plasma Spectrometer, CHIPS or CHIPSAT, was launched. This mission remained active till 2008 and examined the hot gas within the local bubble. However, the most important milestone in the study of this cosmic void was achieved in 2019, when researchers reported the first 3D map of the local bubble using the observations of diffuse interstellar bands. The precise map was made with the data released by Gaia over time. Gaia is an ongoing project that aims to map the position and motion of stars in the Milky Way with the highest accuracy. The mission might not be as famous as the Hubble or the James Webb Space Telescope, but its data has contributed immensely to understanding the Milky Way. Gaia also maps gas and young stars within 650 light-years of the Sun. The observation made by Gaia revealed some interesting information about the bubble and finally provided an answer to its formation mystery. It was concluded that all young stars in star-forming regions lie on the surface of the local bubble, which was likely carved out of the interstellar medium by a series of Type 1 or Type 2 supernova explosions that took place millions of years ago. Supernovas are one of the brightest and most energetic explosions in the universe. A Type 1 supernova occurs in binary star systems in which one of the stars is a white dwarf. The other star could be a red giant, a main sequence star like the Sun, or even a white dwarf. In such a binary system, the white dwarf begins to gravitationally attract the gas from the atmosphere of the red giant towards itself. Most of this sucked-up gas is hydrogen. When it reaches the surface of the incredibly hot white dwarf, it rapidly ignites, thereby creating an explosion, or Type 1 supernova on the star's surface. In contrast, a Type 2 supernova results from the death of a single massive star. When a star can no longer continue nuclear fusion in its core, it starts collapsing under its gravity. As a result, the star's outer layers collapse inwards in a fraction of a second with about 23% of the speed of light. Since the neutron degeneracy pressure halts the collapse of the core, the incoming outer layers rebound back after colliding with the core, causing shock waves, thereby detonating as a Type II supernova. In both cases, when the supernova expands outward, it strikes and compresses the material into which it expands. This results in the creation of dense knots of molecular gas floating in the interstellar medium. These dense regions further collapse under their gravity, thereby forming young stars. Simulations have suggested that the local bubble's history began about 14.4 million years ago, and it is estimated that about 15 supernovas exploded over millions of years to form the local bubble we see today. The current radius of this cavity is 538 light-years, and it is still expanding outwards at a speed of about 6.7 kilometers per second. The solar system has been traveling through this region occupied by the local bubble for the last 5 to 6 million years. It lies precisely in the local interstellar cloud, or LIC, a minor region of comparatively denser material within the bubble. Some theories suggest that when the first supernova exploded, creating the local bubble, the sun was far away from the region. But about 5 million years ago, the sun's orbit around the Milky Way took it into the void, and this is how the sun got placed almost right in the center of the bubble. Probably, the local bubble isn't the only cavity in the Milky Way, and the galaxy is likely full of such bubbles. A detailed study of their location, size, shape, and interaction can help us understand star formation and the evolution of our galaxy in a better way. If you enjoyed this video, please like it and subscribe to our channel for more episodes of the Sunday Discovery series. Also, watch the previous episodes in which we discuss the strange activity on Pluto and the discovery of the farthest galaxy ever seen to date.